Okay, so in this video we're going to have a look at velocity time graphs. Now you're going to notice on some of these graphs that some of the time we're going to have speed on the side, as this one in our first question is going to have, and sometimes it's going to have velocity, okay? Now when it comes to the mathematics behind the way we're going to approach these questions in GCSE maths, it doesn't actually matter whether it says speed or velocity, okay? We're not going to go into the physics behind the difference between speed and velocity, but when it comes to these questions we're going to treat them in exactly the same way. So although it does say velocity time graphs, a lot of these are going to be speed time graphs, okay? But they are going to be treated in exactly the same way. So the way I'm going to run this one is I'm just going to run through a few different questions and one sort of extension-y style question on each element of this topic, because we're going to have a look at distance on a velocity time graph, and we're also going to have a look at acceleration. So I'm going to do the first three questions looking at distance on a velocity time graph, and the next three questions looking at acceleration from a velocity time graph, okay? So what we'll do is I'll timestamp in the description where the acceleration on a velocity time graph starts, just in case that's all that you want to have a look at on these. But otherwise I'm going to run through three of each, and I will link this worksheet as well in the description, so you can print this off and follow along with me if you want. But again, we're just going to get started on this question now. So grab a piece of paper, grab a pen, make some notes. We're going to have a look at this question to kickstart this. So it says the graph shows the speed in meters per second of an object after it started to move. Use three strips of equal width to work out an estimate for the distance travelled between t equals 1 and t equals 4, t being time, which is shown on our bottom axis down here, time. So in terms of actually looking at a velocity time graph, or a speed time graph in this case, we're going to have a look at the distance. Now we know with speed and time that speed equals distance over time, okay? Speed equals distance over time, or in other words, if I want to work out distance, distance is speed times time. Okay, distance equals speed multiplied by time. Now if we have a look at this, because obviously we've got speed on our y-axis and we've got time on our x-axis. Now if I just draw a little shape underneath here, just a little random one, let's go for a rectangle because it's quite nice and easy for our description. The area of a rectangle is length times width. Now in the case of this rectangle here, our width here, it would be a width of 4. It goes from 0 up to 4 on the speed there, and down the bottom it goes from 2 along to, it was meant to go to 5, but I'm not drawing that very well. Let's imagine it just lands on 5 there, and that would be 5. So the area of that rectangle would be 4 times 5 would be 20, and that would represent a distance in this case of meters. Look, it's meters up in our units there, so that would represent 20 meters worth of distance. And obviously that's quite nice when it's a rectangle, but underneath this graph what we're not going to want to do is draw lots of rectangles in. So I'm going to try and do this as accurately as possible, and that's why it says using three strips of equal width. Now we're going to have a look at what happens if we actually split this up into strips. Now it wants me to go between t equals 1 and t equals 4, and we're going to have a look at working out the area of that part of the graph, okay? And it might not be rectangles, but we're going to have a look at what shape is created and how we can actually get the area a little bit more accurately than drawing a load of rectangles underneath. So obviously, just bearing in mind, we're looking at t equals 1 to t equals 4. So t equals 1 is down here, and all I'm going to do is I'm going to draw a straight line up to the graph, and there we go, that's my t equals 1. Now it says it wants it in equal strips because it's going to end here at 4, so this is what we're going to work out the area of, this shape underneath. Now if I actually think about before I actually split that into strips, look, what I could do is I could join those up. There we go, and it makes this shape underneath, and if I join that along down the bottom, and I don't need to draw this line down the bottom, but that shape there is a trapezium. Okay, so actually working out the area of a trapezium, don't forget your formula for that, it's a plus b, or add together the parallel sides, halve it, and times it by the distance between them. Now actually we can make this a lot more accurate by doing it in strips, because if you have a look, and I'll highlight it, look at that massive gap there underneath, all of that distance that we're not going to get if we actually just do it in that one strip there. But we could do that to get an estimate, but this question does actually say to do it in 3 equal strips, so I'm going to get rid of that. I'm going to have a look at how this is going to be a little bit more accurate in 3 strips. Now, 3 strips splits it perfectly along the bottom in 1s. So if I do that, and there we go, we've got 3 strips. We've got this one here, 1, 2, 3. And again, if I just connect those up now, I get one trapezium there, I get another trapezium here, and a third trapezium at the top there. And if you have a look now, you've got a little bit of a gap there, a little bit of a gap there, and a little bit of a gap there. There we go. So it's going to be a lot more accurate than it was just with the one strip, but we'll get rid of that and we'll work out these areas. So I'm going to do this to the side. I'm going to work out the area of each shape. Now before I do that, there's just a couple of lengths that I want to write in. I want to write in what these heights of these trapeziums are, or those parallel sides, and I need to do that as accurately as I can. And again, if you're doing this on the paper, you're probably going to get slightly different answers to me, but I'm going to do it as best as I can on the screen. So the height of that first line on the left of the trapezium that I've labelled as 1, I'm getting that as about a height of 3.4. Let's have a look. Each little square goes up in 0.2, so that would be 3.4. The next one next to that, I've got 6.4, I think it looks like on mine, 6.4. The next one I'm getting around 8.4, and the final one there I'm getting about 9.6. There we go, 9.6, and I think that's relatively accurate there. Now the base of each trapezium is quite nice because it's all a distance of 1. The first one goes from 1 to 2, so that's a distance of 1. 2 to 3 is 1, and 3 to 4 is 1. So that's quite nice that they all have a height, let's say, of the 1 there. Obviously, if you turn this sideways, you can see that the perpendicular sides are those heights in terms of the way that it's drawn. But we just need to be a little bit careful here. So, area of number 1, I'm going to start with. So, to work out the area of trapezium, add together the parallel sides. So we've got 3.4 plus 6.4. We're going to halve that, so I'm just going to write that over 2, and then we're going to times it by the distance between them, which in this case is 1, so we don't actually need to worry about actually doing that. We just need to add together the parallel sides, halve it, and that'll give us our answer there. So what have we got? 3.4 plus 6.4 gives us a total there of 9.8, and dividing that by 2 gives us 4.9. There we go. So in that little trapezium, in our first trapezium, we've got 4.9. Now obviously we need to get the meters correct, and these are normally given to us on the axes there. So it's a speed in meters per second. So meters is going to be our unit there, meters per second. So number 2, our next trapezium, let's have a look. We've got 6.4, the height on the left of that one, plus 8.4. And again, we're going to halve that answer, times it by 1, the distance between them. So 6.4 plus 8.4, and that gives us a total of 14.8. And if we divide that by 2, we get 7.4. There we go. So there's our next distance, 7.4. And then we're going to do our third trapezium. Let's see what we get for that. So we have 8.4 plus 9.6. And again, we're going to divide that by 2. And times it by 1, the distance between them. So 8.4 plus 9.6 is 18, and dividing that by 2 gives you an answer of 9. There we go, so that's 9 meters. Right, so there's our 3 distances for those 3 different trapeziums. All we need to do to get our total distance is add them all together. So we've got 9.4, 4.9, 7.4, and 9 meters, and we just need to add them all together. So 4.9 plus 7.4 plus 9, and that gives us a total distance of 21.3. There we go, so let's write that down, 21.3 meters. Right, there we go, and there's our final answer for that one, 21.3 meters. Now obviously, this is only an estimate, so just thinking about this, and sometimes you might be asked about this, look, we would have to say, look, that these little distances just slightly underneath the curve there are actually missing from the total distance, hence why it says the word estimate there, as this is actually going to be an underestimate because we're missing a little bit of the distance. So some questions may ask you whether it's an under or an overestimate, but in this case, look, you can see quite clearly from the way I've drawn it that this is a bit of an underestimate because we're missing a little bit of the area there. But there we go, that's that question. Let's have a look at a slightly different one. Okay, so in this graph again, it's a speed time graph. We're going to again treat it in the same way as if it said velocity time, but it's sloping in a different sort of direction this time. So we're going to get a slightly different answer in the final part here, but we'll have a look at how that happens. So it says, here is a speed time graph for a car. Work out an estimate for the distance travelled by the car in the first 10 seconds, and this time use 5 strips of equal width. And it says, is your answer an underestimate or an overestimate, and explain why. So like we were explaining on our last question there, we'll have a look at what happens in the case of this shape here. So we're going to do 5 equal strips from 0 to 10. So we're going to finish off over at the 10 there. Let's just highlight that just so we don't go past it by accident. So there's the 10, that's where we're going to finish. So 5 strips of equal width, each one could be a width of 2 then. So let's start splitting this up. So we've got 2, 4, 6, 8, and 10 finishing up there. And if we connect these all up, from 0 as our starting point up to there, we get a little triangle. On our next one, look, we get a nice trapezium again. We get a trapezium on the next one, another trapezium there, and a final trapezium there. There we go. Drawing those in as best as you can using a ruler and a pencil. So again, we can label these up. Rather than label them, I'm just going to do them from from 1 to 5 across. So I'm going to do the triangle to start with. So the triangle, let's have a look. Let's just write in all these lengths again. I would encourage you to do this. They've all got a base of 2, which is quite nice, so we can put all of those in. We just need to get all these heights worked out. So the height of that triangle, I'm getting, let's have a look, every 2 squares is 1. It goes up 10 squares up to 5, so every square is a half. So let's have a look. That first one to me looks like it's about 4 squares, so that's a height of 2. The next one looks like it hits 5, so height of 5. Then we've got a height of, I'm going to have to be a little bit careful when I count these, a height of 9 on the next one. Again, you might get ever so slightly different to me. You will be allowed a range here, just depending on obviously reading those as accurately as you can. And the next one looks like a height of 14 to me, although I can't see it very well underneath my pen. I'll probably have to get rid of that if I want to see it perfectly. Maybe it's 15 actually. I think that's a height of 15. There we go, we'll go for 15. If you've got that slightly different on the paper, then that's fine. And the very last one there, and again I've not drawn the line in perfectly, but it looks like that's 24 to me. There we go, 24. So again, not too much stress here if you're getting slightly different numbers. Obviously you'll be able to see this a lot more accurately than me. Right, so let's work this out then. I'm going to start off with the triangle. Now, I've not got a huge amount of space, let's go for a different colour, we might be able to see a bit better. So number 1, that triangle there. So we've got base times height divided by 2. So we've got 2 times 2, which is 4, divided by 2, which is 2. So let's have a look. And again, this is in metres per second, so our units are going to be metres. So we've got 2 metres there for the first one. The second one, we've got that second trapezium that's got the parallel lengths of 2 and 5. So add together the parallel sides, 2 plus 5, divide it by 2. And because the width or the height is 2 there, we're going to times it by 2. So these are actually probably the best ones to come up here when the base there or the height of the trapezium is 2, because you don't have to bother dividing and timesing by 2 because it's the same thing. So it's just 2 plus 5, which is 7. There we go. So I'm going to use a little bit of a trick now. Rather than dividing by 2 and timesing by 2 and writing all that working out, I'm just going to add together those heights there, or the parallel sides, whichever way we look at it. So there we go, we've got the next one, which is 5 plus 9, and you've got to be very careful because you can obviously only ever apply that trick if it is a height between those sides of 2 or a base of 2, but as it is, let's go with that little trick. So 5 plus 9 is 14, so 14 metres. The next one, number 4, we've got 9 plus 15, there we go, which is 24 metres, and the final one here, our 5th strip there, is 15 plus 24. There we go, and 39 metres. And again, I just want to reiterate, obviously, just be very careful applying that trick. It is purely because each of these lengths down here are 2 that we're able to do that little trick there. And just be very, very careful, because obviously we started off with a triangle there, so we had a slightly different formula for working the area of that out. Obviously it's half base times height. So we've got 2 times 2 divided by 2, or you could have done 1 times 2, just half the base, that's fine. So there we go, we've got all of our distances there. We've got 2, 7, 14, 24 and 39, and we need to add those all together to get our total distance. So I'm just going to do that on a calculator. 2 plus 7 plus 14 plus 24 plus 39, and we add those all together and we get 86 metres. There we go, as our final answer. And again, obviously I've got metres there from our axes with where it says metres per second. Right, so there we go, that is the end of that question. We have got a little bit left to think about, and that is obviously whether it is an under or overestimate. Now for the starting pieces, so it's quite hard to see. You can almost see a little bit of a gap there, and a slightly bigger one here. I didn't draw it in very well, but because obviously the curve is sloping in a slightly different way, our shape's actually going over the top of the line there. So we would say this is an overestimate. There we go, as based on the shapes that we have used, our shape is including an additional area above the curve there that actually isn't going to be included in the real distance. So we've got a slightly overestimate purely because we've got a little bit slightly larger area than we actually should get if we were to draw that perfectly under the curve. But there we go, that is obviously the end of that one. I'm going to have a look at one more question here where we're looking at distance with a velocity time graph or a speed time graph. Right, okay, so here is a speed time graph for a car journey. It says the journey took 100 seconds, which we can see over here on the graph, and it says the car travelled 1.75 kilometres in 100 seconds, work out the value of v. So it doesn't actually tell us the speed up here, it wants us to work out what that speed is up there. Now it says the speed on the side here is in metres per second, so it's a bit odd that it's given us an amount of kilometres, so straight away let's turn that into metres, so 1,750 meters. There we go. Now if we have a look at this graph, obviously we can't actually work out the areas. Now we know the total area there is going to add up to 1,750. Let's just highlight that. 1750 is going to be our total area of these three shapes. And if we have a look, it's not a curved line this time, so this is quite nice. We've got three different shapes there. We've got the shape number 1 here, which is a triangle, shape number 2, which is a rectangle, and shape number 3, which is another triangle. So if we work out the areas of these and use a bit of algebra to do so, and let's see what we get. Now, we could replace the letter V up here with the letter X if you prefer to use algebra with an X, but I'm just going to keep it as a V, obviously as V's been given to us. So the area of that triangle there, that first one, is base times height divided by 2. So the base is 20. So we've got 20 times the height, which is V, so 20V, and we're going to halve that as it's a triangle, so 20V divided by 2. The area of the next one, which we're going to add to that, so we're going to add all these areas together. Let's have a look. The base of that, and let's write these in, that was 20. From 20 to 60 is 40, and from 60 to 100 there is another 40 at the end. So to work out the area of that rectangle, sorry, we're going to do 40, the base, times the height, which is V, so plus 40V. And then for the final one, this final triangle here, treating that in the same way as the first one, we've got base times height, so 40 times V, which is 40V, and again, halving that, so 40V over 2. Again, you could halve the base and then times it by the height if you want, but I'm just going to do it in this way, just a little bit more suitable for people that like to do it in this way as well. So 20V divided by 2 is going to halve that, so 10V. So we've got 10V plus 40V. Half of 40V is 20V. There we go. And if we add those all together, what do we get? We get 10 plus 40 plus 20, which comes out as 70. So there we go, 70V. So 70V is the expression for the total area under this graph, and it says that that is equal to 1750. There we go. So to work out the value of V, we've got to divide by 70. So obviously if you've got a calculator, you can just do that straight away, but let's just divide both sides by 10, so we get 7V equals 175. There you go, and then dividing that by 7, you can do a bit of bus stop for that, but that is 25, V equals 25, there we go. So you may or may not have spotted that that was 25, but you could always do a bit of bus stop and just work that out if you don't have a calculator. So there we go, there's the answer to our question. V has got to be equal to 25. So some of the slightly harder questions on velocity time graphs may involve using a bit of an expression or creating an equation to work out a missing piece, but again, just follow the same normal process. You know that the area underneath is going to equal the distance, so once it's given us the distance, we can work out the expression for the area and set it equal there to the total distance. But there we go, that is the end of distance on a velocity time graph. We're going to have a look at acceleration and some gradients on these now as our second part of this. Okay, so this question says the graph shows the velocity of a parachutist t seconds after leaving a plane. Work out an estimate for the acceleration of the parachutist at t equals 6. Now what we are looking for, acceleration is a change in speed or velocity per second. Okay, that is actually what acceleration is. So if we want to look at a change in velocity here per second, the way to do that is to work out the gradient at a specific point. Now what we don't want to do is we're not looking to work out the average acceleration or the average of anything between these 2 points. We're having a look at an exact acceleration at a particular point in time. And that point in time it's saying is when t equals 6. So t equals 6 is down here. So obviously we just need to very carefully find out where that actually is. So let's just draw a little dotted line going up. There we go. So we want to work it out right there. Okay. So what we're going to do is we're going to work out the gradient at that point, okay, and that's going to show us the change in velocity per second, which is actually acceleration. Okay, that's another way of talking about acceleration. You could say the change in speed per second or the change in velocity per second. Okay, so let's have a look at how we could work out the gradient here. Now this is going to involve drawing a tangent. Now a tangent isn't the nicest thing to draw, to be honest, particularly on one of these curves. It's very fiddly. It's quite difficult to actually get it perfect, but again, don't forget it is saying work out an estimate, okay, and that's because obviously all of our tangents could be ever so slightly different. Very difficult for me to draw on the screen because you definitely need a ruler for this. So what you need to do is you need to get your ruler, and let's just imagine I'm just going to place like a ruler over the curve. Let's imagine it's here. There we go. My rubbish little ruler there that I've drawn in. Now what you need to do is you need to get that tangent so that it just touches at that one particular point there. Now that's going to be quite difficult to do. I would suggest not putting your ruler on top of the curve like I've kind of drawn it in there. Instead I would do your ruler below the curve like this, There we go, and as best as you can make it so that your line just touches that point on the curve there. So what I'm going to do is I'm going to try and do it as best as I can on the screen, but you will be able to do this a lot better, there you go, actually on paper. Now if you have a look, and I'm going to try and show this as best as I can, what you're looking for is around about the same sort of gap here as there is here, just on either side. If that line is going through the curve, or it's going under the curve, or it's obviously going a lot closer to one side, on one side, you're going to want to rub that out and go again, okay? And you just want to sort of practice this a few times till you feel that you're getting it absolutely perfect, okay? So I'm going to do it as best as I can on the screen, but I'm just going to show you the process that you would then take, okay? So I'm going to get rid of these, and obviously once you've got your tangent nice and perfect, there's the same gap either side of the curve at that point where t equals 6, then you obviously can go ahead and actually go about doing this. Now, I'm not too happy about the one that I've drawn here, because obviously t equals 6 is there, and as you can see, my line is too close to the curve on the right hand side of that, and there's a much bigger gap on the left. So I'm going to try and draw this again. Let's have a go. Right, so I want to get that as best as I can. Probably not any better there, but let's just have a look at the process. Right, I'll have one more go. Okay, I'm a little bit happy with that. That looks a lot better. Right, okay, so you've got your tangent drawn in. Now, obviously, you need to know the formula for working out the gradient. So we're going to have a look at the change in y over the change in x, or you might use the terminology rise over run. I quite like this. I quite like just saying rise over run. It's a little bit quicker to say. There we go. So you might know either one of those, but change in y over change in x, which means we're going to have to draw a little right-angled triangle in here. Now, a little tip, because obviously this could be non-calculator, is to try and get the base of that triangle to have a nice whole number, so 1 or 2. So I'm going to try and see if I can make a little triangle with a base of 1 or 2, but obviously it doesn't matter either way. You don't need to stress too much about that. So let's have a look. I'm going to go somewhere from the 4. So from the 4, I'm going to go across here, across to the 6, and then I'm going to go up. There we go. And we need to try and read that as best I can. Now, to be honest, I'd probably rather do this a little bit bigger than making the triangle too small. So let's get rid of that. And rather than doing a base of 2, which would be quite nice because it just means that you've got a nice easy gradient to work out. But I'm going to do this calculator. So I'm going to go across. I'm going to still try and get a whole number though. So I'm going to go across to 8. So from 4 across to 8. There we go. And then I'm going to go up. Right, there we go. So let's write these numbers in. So from 4 across to 8 is a run of 4, so my change in x is 4. And my rise there, I'm going to have to read this very accurately, so I'm going to get I'll get my ruler, go across to here, read that number very carefully, that's 38. And it goes up to, let's have a look if we read that, I'll be really careful not to go wrong on this one, there we go. And that is 55. There we go, so the rise there goes from 38 up to 55, so that is a rise of 17. There we go, so 17. So for this one here, our rise is 17, or our change in y is 17, and our run is 4, or our change in x is 4. So we've got 17 over 4 as our gradient. Now again, obviously if you've not got a calculator, you could write this as a fraction, so you could just convert that into a mixed number. But if you've got a calculator, 17 divided by 4 gives us the answer 4.25. There you go. There we are. And we need to put some units with this. So the units for acceleration, this is in meters per second. So it's just meters per second squared with a little -2 here. And there is our units for acceleration. Right, there we go. Let's just highlight that. So 4.2 meters per second squared. And there is our acceleration at that point in time. Okay, let's have a look at another question. Okay, so this question says, Carol runs a race. The graph shows her speed in meters per second, t seconds after the start of the race. Calculate an estimate for the gradient at t equals 4 and explain what your answer represents. Now, obviously, this type of question, we already know now what the answer represents. If we find where t equals 4, which is just here, there we go, we obviously know that once we work out that gradient, that is going to show her acceleration. So let's just write that in straight away. That shows her acceleration. Right, there we go. So let's work out the acceleration at that point, or the gradient at that point. So t equals 4, again, this is not the nicest for me to draw here, but I'm going to do it as best as I can. Right, there we go. To be honest, actually looking at that, I'm not going to keep drawing this over and over again, but I'm not actually very happy with the fact that there's quite a big gap here, and there's not really much of a gap on the right hand side there. So to be honest, if I had this on paper right now with a ruler and a pencil, I'd be rubbing that out and doing it again. But as we're just running through the process here and having a little practice, I'm going to leave it as it is. I'm just going to go ahead with it, and see what we get. But obviously, if you are following along with me on the paper with this, obviously try and make yours a little bit more accurate than mine there. Now it looks like I've got quite a nice triangle that I can draw in. I'm going to go across from here to here, and again, you can do this however you like. You can make it whatever size you like. You just need to read accurately, but I've just gone along from 3 to 6 there, and I'm going to go up, and I look like I get some quite nice numbers here, so I'm going to stick with this. Now the run there goes from 3, which is just here where the start of that orange line is, along to 6, so that is a run of 3. And it goes at a height from 7 up to 10. If anything, maybe it's just over 10, but 7 to 10, there we go, that gives me a height of 3 as well. There we go. So in this case, I've got a rise over run, or a change in y over change in x. I've got 3 divided by 3, 3 over 3, and that gives me an answer of 1. There you go, metre per second squared. Right, there we go. So there is an answer for this one here. Now I'm just going to do that one more time. I'm going to do this quite quick. I'm going to see if I get the same answer. There we go, because obviously I don't think it was super accurate, so I'm going to have one more go. So let's have another look. Okay, let's just draw as best I can. That is even worse than the last one. Let's have a go at one more time. Okay, maybe one more. There we go, I'm a lot more happy with that one. Let's see if this works. Very difficult to do without a ruler, but there we go. Let's have a look. So let's go across. I'm going to make it a little bit smaller, my triangle this time. We're going to go from here to here, and then I'm going to go up. There we go. So my run there goes from 4 to 6, so that is a run of 2, and my rise there goes from 8 to 10.2 by the looks of it, so that is a rise of 2.2. Right, there we go. So in that, for that working out there, for the second time I've done it, my rise is 2.2, my run is 2, so 2.2 divided by 2 gives me 1.1 meters per second squared. There we go. So I've got a slightly different answer there, so you can see how obviously just changing the gradient slightly is going to slightly change your answer. But these sorts of exam questions, you are going to have an allowed amount of range there, so it's going to be somewhere between 1 and 1.2 or something like that. Okay, but obviously you just want to do this as best as you can. Make sure you show you're working out, make sure you draw your tangent in nice and clear, make sure you show where you've got your numbers, make sure you show your rise over run, write down change in y over change in x, show those numbers. Okay, and then even if your tangent isn't great, you're not going to lose more than 1 mark on a question like this. But obviously just a little bit of practice getting those tangents perfect. Right, let's have a look at another question then. Okay, so this question says, here is the velocity time graph of a car for 50 seconds. Work out the average acceleration during the 50 seconds and estimate the time during the 50 seconds when the instantaneous acceleration is equal to the average acceleration. Now we're going to have a look at these two questions separately. So the first one says, work out the average acceleration during the 50 seconds. So this is very different to what we're doing. We're not looking at the acceleration at a specific point in time. We're looking at the average. Now, if we want to have a look at the average, we want to go from the start to the end and just see what the average acceleration was. So we're going to have a look at what the average gradient is from there to there. And that's easy enough to do because obviously we're just drawing a nice triangle with a nice straight line there. So all we want to do is work out what's the rise, what's the run. So coming down, that gives us a rise there, or a change in y of 30. And if we look at our run going along the bottom, it goes from 0 along to 50. There we go, so that's 50. So in terms of our average acceleration there, we've got a change in y of 30, change in x of 50, and 30 over 50 equals 0.6 meters per second squared. There we go, so there is our average acceleration for this question. Let's just highlight that. 0.6 meters per second squared. Now the next part of this question says, and obviously just before we move on to that, just be very careful because this is only something you will ever do when it says work out the average acceleration. Okay, so we're basically just working out the gradient from start to finish and taking an average rather than at one specific point. Because obviously if you have a look at this graph, the acceleration increases as the gradient increases going up, and then the acceleration slows down as we move slowly towards that side there. Okay, so obviously we're just working out that average in between, but let's have a look at this next part. It says estimate the time during the 50 seconds when the instantaneous acceleration is equal to the average acceleration. So we've already got the average acceleration, it's 0.6. The instantaneous acceleration is at a specific instant or specific moment in time. So what we're having a look at is where on this graph is the gradient of that tangent that we could draw in going to be equal to that line that I've just drawn in there. So it's going to benefit me obviously drawing that line in, because all I'd really need to do is get my ruler at this point, and I just need to see where my ruler would be pointing in the same direction of this line. So obviously you've already joined that up nice and neatly with a ruler, but all I want to do is get that ruler. Now what I'm going to try and do, I don't know if this is going to work, but I'm going to cut this line out and see if I can move it. Okay, I can, brilliant. So you've got this line, you want to make your ruler in the same direction. So if I move this around the curve, look, it gets to this sort of point. If I just touch it on the curve there, I think if I drop that down a little bit more, that looks around perfect there. I can't get it perfect. When I release it, it kind of jumps. There we go. So that there has given me the same, obviously it's the same direction because I've moved the line that I'd already drawn, but what you're looking obviously is to create a parallel line that has exactly the same gradient at that point. So if we have a look, that's obviously met the tangent at this point right here, and if I go down from there, let's have a look, it's around about there. So if I go down, that there is, it goes up in 1, so that there is going to be 12 seconds. There we go, 12 seconds. There we are. And obviously that line there that I've dragged over is definitely going to have exactly the same gradient as the original line, because obviously I just moved the exact same line there. But you would just need to get a ruler and obviously try and create as best as you can a perfect parallel line to that one. Obviously that is just touching a tangent at a point there. Okay, so there we go. That's the final answer for that part of the question there. That is the point there at 12 seconds. Obviously it is only an estimate because we can only draw these in as best as we can, but that is going to be where my instantaneous acceleration is equal to the average acceleration, because at that point there, if I was to draw a gradient in, I would have the gradient of 0.6 meters per second squared again. And to be honest, for a question like this, I would probably just go about actually drawing a bit of a triangle in and actually showing the gradient at that point as well. But obviously, as it's a line that I've already dragged over, I'm not going to do that because obviously you already know what that gradient is. Okay, but there we go. That is something else to be looking at with velocity time graphs. That's going to be the end of those questions there. So I hope you found that useful. I hope it was helpful. Obviously, please like, please comment, please subscribe, and I'll see you for the next one.